Hey everybody, Shawn here from the Automation Blog and School, and in this episode of the Automation Podcast, I sit down with Nathan Eisel from SMC to learn about the world's most popular Ethernet field bus, EtherCAT. Nathan, thank you for coming on the Automation Podcast to tell us all about EtherCAT. Can you introduce yourself to our audience?
Yes, thank you for having me. My name is Nathan Eisel. I'm currently working for SMC, Corporation of America, the pneumatics people. And I work with them or for them as the a national new product development manager. So I'm on the new stuff team with a national scope. And so yeah, that I have to look at different technologies every day, and EtherCAT is one of those new up-and-coming technologies that a lot of people have a lot of questions about.
Excellent. Well, I'm looking forward to learning all about it, and I appreciate you coming on the show to tell us.
You bet, you bet. So let's get this thing rolling. So again, SMC and EtherCAT so EtherCAT, we can look at that as it's a field bus, right? So it's an Ethernet based field bus, like Profinet or like SIP styles, so your Ethernet IP and things like that. So it's along the same lines. In fact, it uses the same technologies, like the same Cat5 cables, the same RJ45 jacks. But inside, the way that the network is structured and the way that the packaging architecture works is very, very different. So a lot of people have questions about that, and we're going to go through that today. So a little bit about myself before we really jump into the technology. So why am I here, and how did I get here, right? So where are we going and how did I get here? So I have a kind of a unique history. After getting an IT degree, the first time going through college, I actually went out there, and this is going to date me a little bit. So when the .com bubble burst, was right when I was graduating college the first time. And so I went out into the marketplace and with an IT degree, and it just wasn't a super hot market. And I got talked into, hey, what would happen if you were to combine your IT degree with a mechatronics degree? So automation, mechatronics, and I think the listening audience, everybody knows what that is. It's mechanical meets electrical meets controls, and you kind of wrap all that up into one term, and that's mechatronics. And so that's exactly what I did. Is I went back and got a mechatronics degree, married it to an IT degree, and that was in 2006. And since then, I've been working for factory direct vendors in the controls world. And started out cutting my teeth, and now here I am at SMC with a national scope on new products. So working with different customers on what is tomorrow's technology and how do we adopt that, how do we adapt that better into what's coming up. So something interesting that the audience, I'd like everybody to know, full disclosure. So SMC, we have a very, very big product line, mostly in the pneumatics world, in automation, over 1 million different variants, but we don't sell any PLCs. We don't sell any controllers or, master scanner cards, things like that. We are always on the other side of that. So we're on the slave side or the subordinate side. So I just wanted to make sure everybody knows that, because we're going to go into technology like EtherCAT and hey, why is this guy talking about EtherCAT? Because they don't even sell it. Well, what I found is that the knowledge is power, and if you understand how the entire picture is supposed to look, then you know better how your little piece operates. So that's really what it is. Like I mentioned before, EtherCAT is on the scene, has been for quite a while, but it's just picking up a lot of steam, and it's right now the second most popular by volume field bus in North America, and it's the #1 fastest growing field bus for SMC. Now these are SMC statistics, so it might be different for a different company, but that's really what I'm seeing from the inside of my company looking out. That's what I'm seeing. So this was really important, and again, thank you for the opportunity to come along. when I was putting this information together, I just wanted to make sure that this was not my opinion. Like, I wanted to make sure that this is fact data, and just present it in a way that, hey, everything is factual. Yes, I might have my personal opinions, but my personal opinions are not going to be part of this presentation, because I wanted to just lay out the facts as the governing bodies state them. Now, the governing bodies in this, so people, I think, are very familiar with the ODVA, which is the governing body of like DeviceNet, ControlNet, Ethernet IP. Iona is the governing body of like all things Profi based, so Profibus, Profinet, Profisafe for safety networks and things. Well, this isn't really any different. This is the EtherCAT.org, or the ETG, the EtherCAT Technology Group, is the governing body for the EtherCAT technology. And so I reached out to them and asked, I said, hey, I'm doing a presentation to many people, a lot of people, in fact, and I just want to make sure I have my facts correct, because there's no room for fudging on this. I just want to make sure I'm correct. And so they were gracious enough to support me. They were able to support me, one, because SMC, my company, is a member of the ETG, and later on here I'm gonna go into just different memberships, like just to show, hey, this isn't just a one vendor wonder kind of thing. This is really growing worldwide. But so anyways, I just wanted to let everybody know, full disclosure, this is not my opinion, even though Lord knows I have opinions, but this isn't one of them. This is fact, right from the governing body there. So ETG was founded in 2003. So again, this isn't, a technology that came out, is as far as, I was just going to mention something that's going on, with cryptocurrencies and things, and it's all brand new. And this isn't one of that. This has been around since 2003. So it's quite established. And in fact, you can, if you don't believe me, look it up yourself. It's just, EtherCAT .org. And I have a link on the PowerPoint, so it can't be confused. So
now I want to jump in, Nathan, just for a second.
Yes,
for
sir.
the podcast audience, those listening on iTunes and Google and Spotify and all the different services, there was a great slide there that Nathan had that showed the entire history of EtherCAT. So those who are watching on YouTube or the automationblog.com, you guys just saw that. But for those purely listening, if you ever want to see the full history of EtherCAT from inception to today, that was a phenomenal slide. And thank you for sharing that with us, Nathan.
Oh, you're very welcome, and I apologize. I'm so used to presenting on a live Teams audience nowadays. Given what the pandemic that we're living in, all these. So I apologize for that. Thank you. I'll try to do a better job describing what I'm looking at. So yeah, thank you so much. So again, a definition, and I don't want to do a dictation of this is what this means, ... blah blah. I don't really want to go through that, but the bigger idea is, so EtherCAT is a field bus, so it's an industrial field bus like Ethernet IP. It came about in 2003. The cool thing is it's an open technology, so anybody's allowed to implement it or use it. That's kind of neat. And we're going to go into that, the membership and all this, and it isn't this, again, this is not a sales pitch to sell EtherCAT. This is just a show. Look, this isn't not I was going to say something, a one-trick pony kind of thing. This is not that. This is open and standardized. So some of the things that make EtherCAT stand out among the rest. So again, it is an Ethernet-based field bus. So again, same Cat5, same RJ45 connectors, things like that. But there are things that stand out. Exceptional performance. We're going to get into that. How do we determine what the performance is, and what is the around the horn cycle time kind of things. And I do have some hard information on that, kind of a compare and contrast, and then explaining why it's different. Flexible technologies. We can get into star, line, tree, whatever different topology your machine or the machine needs, EtherCAT can adapt to that, and we'll show you how that works. Again, with the same cabling, same Cat5, same RJ45 things, it's very simple and robust. We're going to get into the simple and robust. The simple part is, hey, it's all the same piece parts, right? So the cabling is the same, the connectors are the same, termination is the same as any other regular Ethernet, field bus or not, regular Ethernet standard. So the IEEE 802.3 standard is what this uses. So yeah, that lends to a whole, smattering of you don't need to go to this vendor for your RJ45 connector. You can go to whatever vendor you'd like, as long as it's an RJ45 connector, right? So that's kind of the idea there. And again, that goes into affordability, and we can all kind of connect the dots on that. And of course, last but certainly not least, having the ability to have integrated safety across this field bus. As we all know, this is not a integrated safety presentation. This is just EtherCAT, but integrated safety is there, and it's there on all major platforms. So your Ethernet IPs with SIP safety, the Profinet with ProfiSafe safety, and of course EtherCAT with they call it FSOE or failsafe over EtherCAT is also there. So it covers a lot of bases, and we're going to get through the whole how does it work. Well, if you have some questions on, maybe you haven't heard this before, or maybe you've heard it, seen it at a trade show, but have never seen it in action, like, that EtherCAT stuff, that's only for the high-end scientific machines, or it's only for the pharma industry, and I work for packaging industry, and so it doesn't really apply. And that's not exactly true. On the screen, again, I have listed, and I'm not going to read it out for everybody. If you wanted to view it, like Shawn said, you can go ahead and log in and view it. But it really goes through a smattering of anything from, something unique like tunnel control systems, sawmills, welding machines, and then of course all the common ones. Anything in the pharma industry, anything in the food and packaging industry, automotive, robotics, and anything end of arm tooling, different synchronicity issues between different robots and different cells. That's really where this stands out. However, it can work for anything that you can imagine. And really, flat glass manufacturing equipment. And again, this is all stuff posted from ETG. So I didn't just Google this. This is official. So yeah, this technology is used in a lot of different places.
I think, Nathan, we could really sum up the slide by saying that the EtherCAT organization really feels like they can do any application. I'm looking at this list. This is the same list you'd see from any major automation vendor. So,
right.
I think I would summarize it just for the podcast audience. This is the same application list you would see any major industrial vendor. It's pretty much any application. I can't think of one that's not on this list. Pulp and paper, robotics. It's all there.
Farming machinery, it's like okay, sure. So absolutely. But how does this all work, right? And so I kind of wanted to do a little bit of a compare and contrast, because for me personally, the way I learn is, hey, I know how X works. If I know how X works and somebody can compare that with Y, then I now can sort of kind of understand why. So that's what we're doing here. On the screen, what we're looking at is just a regular Ethernet switch. The switch has 4 ports coming in and 1 port coming out, just for simplicity. And what we're talking about is switch buffering delays, and how does it actually work? And a lot of people may not know that there's a technology called store and forward. Sometimes that's used, sometimes that's not. But the way that it works is that there's 4 different messages that come into the switch. The switch then combines those messages and then sends them all out one. So it'd be like, you have 4, valve banks, or 4, a valve bank and some IO and something else, a servo drive. and they're all coming in, and it waits for all those messages to get in. Then it sends the whole lot of them to the master scanner or the like, something like that. That's what we're looking at, right? Well, that builds up internal delays, and it's not the delay of the particular vendor that you're using. It's just the technology. This is how it works, right? That's how it works in a switch. And so it's a cool animation that some of the podcast listeners, I'm sorry, you won't be able to see it, but on the second animation is really the same thing. So the first one we were looking at maybe like a star topology type of deal, to where you have everything hardwired right to a switch, and then everything from that switch goes to one scanner card. Now we're looking at a different topology, to where we have more of a line topology. So packet comes in to a switch, and then to a drive, and then it goes to 4 different drives, and it's all daisy chaining along. And you kind of get the idea of, with each time that it daisy chains, because of the way that the packeting works, the packet has to traverse all the way through the 7 layers of the OSI model, and has to go and get encapsulated and then decapsulated every time it goes up and down that stack. And all of that takes time. So what we're looking at here really, and again, I'm absolutely not here to pick on anything. I just wanted to compare and contrast X versus Y. Again, that's how my brain works. And so really what we're looking at is these they call it a stack delay. So these stack delays all the way from the physical level to the application level. So 7 layers of the OSI model, which is an IEEE 802.3 standard. And again, like I'm rattling off all these standards and all this. This is just, this is what everything is based on. So Ethernet IP, Profinet, EtherCAT, all of these Ethernet-based technologies. That's what I mean by Ethernet-based, right? It's IEEE 802.3. So yeah. So with Ethernet IP and Profinet, there's a ton of stuff that goes on. So let's look at this as your 7 layers. Layer number 1 is the physical layer. Layer number 7 is the application layer. And so physical data link, everybody knows what a data link is. If you know what a MAC address is, that's data link layer. The layer number 3 is your network layer. Network layer is where your IP address is stored and things like that. And then after it gets the routable IP address, we'll call it, layers 4 through 7 are more to deal with encapsulation, decapsulation in different parts of the datagram, are read in, read out for different network appliances, routing, things like that. Well, that's how this works. And so there's a ton of stuff that goes on between layers 3 and 7 that Ethernet IP and in Profinet, they have to use. So in those words, and again, I'm comparing and contrasting just as I know, and please, correct me if I'm wrong, but the way that it works is you have to have the scanner card, and that scanner card is just going as hard as it can, decapsulating or decoding and encoding these messages, right? And so I think the way that Ethernet IP works is that you buy your scanner card based on the message load and how many messages you're planning on getting per minute, per second, per whatever it is, and because that's how much horsepower that the scanner card has, because it has to read up all these messages and deal with them and so on, and that's really where there's a lot of delay in that. Okay, so all that being said, EtherCAT completely removes layers 3 through 6. So all of that stuff in the middle, it doesn't even bother with it. Now, you're saying, wait a minute, if that's part of this 7-layer OSI model as part of IEEE 802.3, and you're removing all that stuff, how does that still comply? Like, well, you can't just cut stuff out. Well, in the next couple slides, we'll get into how the packet works. And really what it's taking out is a lot of the overhead, right? So it's the same packet, it's the same technology, it's just the stuff in the middle is removed, because in industrial applications, generally you don't need that stuff. That's what the EtherCAT people have found, is you just don't need it. So that's...
Well, let me, Nathan, I want to jump in here for the podcast audience. Nathan, I'm going to jump in here for a second for the podcast audience. This is a phenomenal slide, but for those who you may be listening while you're driving or working out, think of it this way, like Ethernet IP, if you're familiar with it, right? Your scanner has to be able to, well, bridge, across the backplane to another card. An Ethernet IP scanner would be able to seamlessly bridge to control net or device net or another network, right? It also has the capability to do implicit and explicit messaging. It has the ability to encapsulate older PCQ messages into CIP. It has all these things it can do. It can do TCP or UDP type of messaging, and of course, you can give it an IP address. So it's a number of different ways. That's the layer 3 through 6 that Nathan is talking about. That's stuff that's not needed in EtherCAT. So, did I do a good job explaining that?
Absolutely. That is absolutely spot on, Shawn. That's exactly what I was trying to get to, just in a really roundabout way, maybe.
No, I thought I'm just trying. This slide is just phenomenal. And for those who might be in the car, I just kind of wanted to add that little extra to it.
Sure. No, absolutely. Absolutely. So this is really, and thank you for picking up on that. It's a subtle thing. But if you know what you're talking about, or you know what you're looking at, it's not so subtle, right? It's a lot of impact going on here. And again, I got to preface that, look, I'm not here to beat up on anybody or anything. It's just a compare against, right? So, like you said, people really do understand how master scanners work in Ethernet IP, and maybe even some type of Profinet scanner, because it's from 10,000 feet, it's very similar. So yeah, there's a lot of delay time, and really what I'm kind of bracing you for is the ridiculous. I'll steal the term ridiculous type of round the horn propagation delay or lack thereof in milliseconds. How fast of a cycle time do we need to get, or can EtherCAT achieve? And then we're going to get there through the compare and contrast. So again, from Profibus International, these are again stuff I can't make up. And Profibus International is saying that real-time Profinet, we're looking at cycle times between 5 milliseconds and 10 milliseconds. That's really where they're at now. When we get into IRT in Profinet, that the cycle times are reduced more. However, with IRT, it's my understanding, and again, I'm not the expert, and I could be wrong, but I believe that there is some specialty hardware that you need to have in order to get like the 1 millisecond, 2 milliseconds, or even sub-millisecond kind of turnaround with IRT. With Ethernet IP, it's kind of the same story. So and this is a clip right from Rockwell. So again, I don't want to send out false propaganda and stuff like that. And again, I'm not picking on anything. It's just, hey, this is how that manufacturer says this works. And so with Ethernet IP, we're looking at something that's very common of like 8 milliseconds or 20 milliseconds. And there's quite a bit of network bandwidth utilization. So what does that mean? Well, if you're looking at like a freeway, think about it like this: your bandwidth utilization, the 100 megabit per second. You got a 4-lane freeway that's all going north, and it's got 4 cars on it. Well, those 4 cars can go really, really fast because there's a lot of open road for those 4 cars. But if you put 100,000 cars on that same stretch of road, things are going to be moving a lot slower. It's the same bandwidth. It's just a lot more stuff, a lot more data on that freeway, right? So that's where we get into network bandwidth utilization and things that 3-way analogy usually works. And so that goes back to, okay, so at the end of the freeway, it all, traffic cones down into 1 because, we're doing road work or road construction. And then it really is a delay. And that's that traffic cone down into 1 point that could be looked at as your master scanner card, things like that, to where it has to encode and decode every single message every single time. And that thing is just working its tail off, but it still can only get so many cars through because it's 1 lane, right? So that's kind of the idea behind it. There's a really cool picture, and again, Shawn, I hope you comment on this. I thought this picture was really cool. So what we're looking at is an open-wheeled race car, like an Indy car. These things make incredible amounts of horsepower. So the horsepower is absolutely there, but I'm a huge race fan, and so that's why I like this screen. It doesn't matter how much horsepower you make if you can't put that power to the ground and get from A to B. It doesn't matter how much horsepower you have, you can't put it on the ground, right? So the analogy is no matter how powerful your PLC is, the latest and the greatest with different, core, dual core, quad core processing units and different things that are coming out, which is fantastic and amazing. If you can't take that processing power and put it out on the wire, that's like a race car having a tremendous amount of horsepower. You just can't put the power on the ground, right? And so what we're looking at is this open-wheeled race car, an Indy car with bicycle rims on it for tires, showing the analogy that you can't put the power to the ground. So you got to be aware of that, right? So even though people want to say, "Hey, I got this, ridiculous quad core or whatever," that's cool, great, that is fantastic. Now, how do we get that information out to the field devices, right? And what is the turnaround time on that? What is your network latency? Things like that. So yeah, I just thought that was kind of a cool analogy. Did I do a good job describing that, Shawn?
No, that's excellent.
I just thought it was kind of a cute little thing, just throw that in there. But so this is where we get into the controversy. This is normally where I get like, rotten vegetables thrown at me on stage and things. This is where we get into what can EtherCAT do. We just went through what the other guys can do. And that was based on information from their own websites and things. So I'm not making it up. And this is where it gets a little bit crazy. So EtherCAT, the folks over at ETG, say that 1,000 distributed IOs can be updated in 30 microseconds, for example, or 100 servo drives updated in 100 microseconds. Now, this isn't milliseconds, this is microseconds. So this is sub 1 millisecond stuff. And so that's why I took so much time explaining how the stacking delays and switching delays and things like that works, because EtherCAT doesn't use that. They just took that out of the standard and opted to not use it. In the next slide, we're going to get into how that all happened. But just to let everybody know, the performance side is absolutely incredible. And so it's EtherCAT right down to the device, so the I/O device or the servo drive device itself, and that's why it's so unique. Now, you don't have to. You absolutely do not have to run your what was one of those examples? A farming machinery implement. You don't need to run that thing at 30 microseconds. I'm pretty sure a seed can go in the ground slower than that. But if you need to, when you're creating pharmaceuticals or you're creating fusion or fission in plastics and different welding operations and things where you do need crazy amounts of high-speed loop feedback, this is absolutely the one for you.
I want to key on one thing that you had there that for the Rockwell listeners was that the EtherCAT is going directly to the slice I/O. And there's no sub bus. So a lot of people may not be aware that, like, when you go through point IO, you're coming in Ethernet and you're going, really the backplane is device net. So there is a hop there that happens. And so in addition to all the other phenomenal benefits and the rich data you have available, it's also that hop. That's another part of, the delay you're having. That's one hop that EtherCAT, according to this slide, does not have to make that lends to the high speed.
That is absolutely correct, Shawn. Absolutely, that's how it's designed. Now, a little bit of insider trading information here. I do know that there are some vendors, and again, I keep promising this giant vendor list, and we'll get to that. But there are some vendors in the EtherCAT standard. There is a provision to build in exactly what you just described. Let's maybe call it a secondary type controller or a secondary bus, like you just described. EtherCAT can also do that. Yes, it has the ability to do that. However, as you very eloquently described, it does add delay, and it does add a little bit of complexity, maybe even a little bit of cost associated with that. So you don't need to do that, but if you have to, it is available, right? So so absolutely, and I do know some other devices from other vendors that they had some proprietary, doohickey that they had to build kind of a bus, so EtherCAT to it, because the rest of the network was EtherCAT, and then their proprietary doohickey they just built an interface for kind of thing, and so it will still do that, but the idea is you don't need to, right? You can go directly to your microprocessor right from EtherCAT, right? So that's kind of meat and potatoes. That's really what we're talking about.
Yeah, and just for the old timers out there, you may remember the 1734 PDN. That was actually, that just put the IO cards directly on the device net. There was no sub bus in that. So that kind of, it was still much slower, but that kind of mentality where you had an adapter that just put everything right on the same network. And
Right.
so for the old timers, Rockwell old timers remember that old PDN device versus an ADN. But go ahead. I'm sorry. I didn't mean to interrupt.
Oh, no. This is great. It's a great discussion. No, so earlier I was talking about, okay, so yes, this is an IEEE standard with the 7-layer OSI model, and it's all based on an Ethernet standard. But wait a minute, but these guys cut out a lot of functionality. How does that all work, and how does it still comply to the standard? Well, so what we're looking at on the screen is for those of you in your car or whatever, it's really riveting information on how an EtherCAT packet gets built. It's the really riveting stuff. Yeah, it's kind of the stuff that we all look at and go, oh, that's pretty neat. Flip the page, because it really doesn't affect us, because generally as users of these appliances, we don't get a chance to actually build the frame for this EtherCAT frame or Ethernet frame. So, but to understand how it works, that's why I went ahead and wanted to show is yes, even though some of those functionalities have been removed, everything still fits in the same datagram. So the packet out there on the wire looks exactly like, it is an Ethernet IEEE 802.3 packet. So we haven't changed the packaging, which is why the cabling and connectors and all these things, that all still works exactly the same, because we haven't changed the frame, we haven't changed the packet. How do we put so much stuff into one packet so we can update 100 servo axes in 100 microseconds? How does it work? Well, because the frame is so efficient, we've taken out all the overhead, is what that amounts to, right? So we've removed the overhead that industrial applications don't really need, as far as checking your email and having an emoticon singing and dancing and playing some cymbals. Yeah, sure, you might need some of that functionality in that case. Pretty sure a servo axis does not need an emoticon with bashing cymbals and things like that. So those features are removed, and the packet is optimized. Packet is optimized in order to get the most data you can through one packet, and the way that packet traverses the network is very unique. We're going to go into that next. But so what we're looking at on our screen right now is master scanner card with a bunch of different devices. So we have I/O devices, we have servo devices, and these might be in different pieces of the machine, and they're all kind of segregated. So the logical segregation, we have some motion, we have some left-hand side stuff, some right-hand side stuff, and some in-feeder stuff, right? And that's all segregated logically in the controller, but as it comes out on the network, it's all put back together, so it's very, very efficient, right? So that's really what it's hard to get your head wrapped around if you've never seen that before, but that's the magic, right? How do we update so 100 servos in 100 microseconds? That's magic. It can't be true. No, it is true, and this is actually the magic, right? This is actually how it's done. kind of lifting up the curtain a little bit on this. So the real key here is, and the next slide will be animated, so the people that view this will get a better idea. But imagine like a train. So I used a freeway analogy earlier, which is 100% still the truth. But now think about a train, and this train goes from from A to B, and there's 10 stops in between, and it's very efficient. The train just stops for maybe less than a minute, and this is for people and everything. And for people get on, people get off, it goes to the next. People get on, people get off, goes to the next. People get on, so on. But it's one train. That's how the EtherCAT datagram looks. Is it's one train that goes a bunch of different stops, and actually it doesn't actually stop. The way that the interfacing works at a microcircuit level is that the packet doesn't actually stop. It unloads and reloads on the fly. So they call it EtherCAT on the fly, and that's how this a massive amount of data is being able to be updated so quickly. It isn't hundreds and thousands of messages. It's one or two messages that are very, very efficiently put together, and that the slaves can read in, read out. There's only one master to it's a one to many. So one scanner master to many subordinate slaves. And each one knows where they are in the network, and each one knows its address in the packet. As the packet comes by, it puts updates for inputs on, and it gets delivered updates for outputs as the packet traverses through the network. So it's kind of neat how that all works. We're looking at an animation right now, and like I said, just imagine, and maybe Shawn, you can give your analogy on this too after you see it working, but it really is kind of like a train that goes through many different stops, and but for people, obviously for safety, it has to stop. But electronics, it doesn't have to actually stop, get read in, processed, and then read back out, as a traditional Ethernet IP or Profinet network has to do, because it's one packet. It doesn't have to be read in, yep, nope, that's not for me. Read in, yep, nope, that's not for me. Read in, okay, that's for me. Decode it and figure out what we need to do with it. All of these slaves know exactly what memory is for them, and it's updated on the fly. So it's exactly this mechanism and the very efficient packetization, or the way that the datagram is formed, that makes it so unique and makes it so efficient.
Yeah, and I'll just add that this is an excellent graphic, and you can definitely see by looking at this, we're not talking, correct me if I'm wrong, Nathan, we're not talking produce consume. So we're not talking, on a produce consume network, a device just spits out its data, and whoever wants it can take it. And the consumer can take it if they want to take it, or they can ignore it. In this case, we have a packet that has multiple devices' information in it. And as a packet stops at each device, they take their information out and put any information in. And then the train, like you said, the train goes to the next device. So there's not these multiple, it's not like a bunch of taxis or, cars just making single trips with people on them, right? It's not like a bus, a bus for every device. This is one train for the whole network. Well, and there would be multiple packets. And I think an important point you brought up on the previous slide was the fact that, you may be thinking, okay, so I have each device is sharing this packet, so I won't be able to share a lot of data. And one of the things that comes up a lot when we talk field bus is, that would be horrible if you couldn't have a device that has lots of information, be able to pass it. And I think in the previous slide, you had 60K worth of bytes.
Yes,
That's a lot
correct.
of data. That's a lot of data. 60,000 bytes. 1 bit to 60,000 bytes. So
right.
if a device has a lot of data, it can share it across multiple packets, right, or multiple frames, right? So that's an important point. So of course it'll take longer to send more data, but you're not limited to only very simple devices like discrete I/O cards.
That's exactly right. So the big thing here is the 60K bytes. That is per slave. So that's not per network. that's per slave. So you can have many slaves out there. Now, I think that the provision for 60,000 bytes per slave, I think that is the absolute high end. Normal devices don't consume anything close to that. However, it's been provisioned. So if a vendor wants to come out with something like that, hey, they have the utilization, the bandwidth to do that, right? It's already been spec'd. So yeah, and you're absolutely right. The datagram or the frames that are traversing the network, your taxi analogy was perfect. So you have one train delivering all the messages to all of the devices rather than a taxi cab or multiple taxi cabs, because maybe there's multiple messages per device all kind of running around out there. And if you use that same analogy, a train tracks versus a freeway, train tracks are, there's one train on the tracks versus, a bunch of taxis all trying to run around in the same streets, and they're competing for the same bandwidth, right? So absolutely. Now, your question about the, if there, can I send out multiple frames? And the answer is absolutely 100% yes. You can send out multiple frames, and it's like sending out two bullet trains, one behind the other one. And then that's all provisioned as the network is being started up. It's the Abbott and Costello thing. Who's on first? What's on second, third base? So it's the network is queried when it first starts up and says, all right, this is how I'm configured. What's actually out there? And so there's a querying message that goes out and gets the who's on first, what's on second, right? Comes back and says, all right, yep, that lines up. Here's your memory. Here's, Mr. Device number 8. You have your data is in this packet and in this spot in this packet, right? And that's how it's organized. So that's how it's so efficient. But like I said, yes, absolutely, we can have multi frames out there at the same time, but they're sent out one after the other one. So with like zero delay, because it's a train and it's on its own tracks. You can send out two bullet trains, very, 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 very close to the same time. So the engine and the caboose are right up next to each other type of situation. So
I think I saw too that you said there was a provision for trigger based or asynchronous, maybe an alarm occurs type of
the data that must be updated cyclically every X. So every 1 millisecond, every 500 microseconds, whatever it is. Every 10 milliseconds, certainly. But also, there's also provisions in that datagram for out of process data. So the out of process data, that happens as you can think, okay, we're going to be using this train analogy. So the process data is the high-speed bullet trains. And they're running along, and we know when those things run, right? So we know because it's all scheduled, just like ControlNet actually. Your packages are all scheduled, and so we know when they're going to go out. And also kind of like ControlNet too. So because we know when they're scheduled, we can then, in between sending out those packages, we can have out of process data. If you want to get the temperature or the serial number off of some device, or something that you'd need to use like explicit messaging for. So we have our implicit, these are not implicit, but you could think about it as an implicit message going around the horn every 10 milliseconds, and then sending an explicit message as out of process data. This also has provisions for that too. So if you needed to in your application, hey, I need this much, these many nodes to have my process data that needs to cyclically be updated real time, deterministically, all these things. But then I have, hey, I want to check this, or I want to look at that, or things that are not as critical, we'll call them. You can always send an explicit message. That's the same idea, but it's an out of process message. The EtherCAT folks, they call it a COE query. So a CAN over EtherCAT query. And you can change different parameters, things like that. Like I said, the best analogy is it's like an explicit message to where you can change a parameter or something inside of a drive or whatever, but it's not competing with the process data. So your actual position, your set position, velocity, those things. So yeah, no, great question, Shawn. Great question. Now, part of this, the way the packet works and the way that it traverses the network, because it doesn't matter, the packet needs to go around the horn no matter what, right? So like ControlNet or like other networks that are a ring, this is also inherently a ring. Maybe you just don't wire it like a ring. So you think, okay, yeah, this is a star topology, or this is a line topology, or daisy chaining, which physically it is, but technically on the inside and logically, it's always going to be a ring, because EtherCAT is a self-terminating network. So when the packet goes and it says, hey, I need to go to the next, nope, there is no next one. Okay, I will back through the network again, because it's one train on the tracks at a time. I can go, basically put the train in reverse, go all the way back through the network the same way that I came through, and boom, I come back. So it makes a full circle. Now that being said, because that's how the technology works, physically, it really does not matter how you line stuff up. If it's convenient to do a daisy chain configuration, no switches, things like that, okay, cool, that's no problem. You can just wire, EtherCAT in to EtherCAT out jack on the same device. That's okay. Maybe you do have a device at the end of the line, but then, hey, you wanted to branch off, do a branch further up. Okay, that's fine too. It all depends on what the devices are in the network and how did that vendor comply to the standard. Did they develop so they have all 4 ports of the EtherCAT chip, or did they use 2 ports, or did they use 3 ports? So that really depends on the EtherCAT technology is provisioned for that. It kind of depends on the vendor. And in order to get ODVA compliance, of course, just like ODVA compliance, to get ETG compliance, you have to comply. And so if you say your device can daisy chain, it can do this, it can do that. Okay, well, it has to do that in order to be validated. So so the network, what we're looking at is drop line, a star, a tree, a regular line like daisy chain. The physical topology, again, doesn't really matter, because the technology behind it, underneath the hood, is always making a big loop anyways. So
it sounds like it's a loop of nodes. So regardless of the physical, regardless of the roads between the destinations, the postal truck still has to go to every house, right?
that's exactly right.
In the EtherCAT, it sounds like it's going to make its round of all the nodes it has on its network, regardless of the topology. Whether it's a dead end street or it's a an off ramp or on ramp, which makes a lot of sense. You have a list of nodes that's part of the network, and it's going to hit all of them.
That's exactly right. That's exactly right. And one other thing before we move on from topology, I kind of wanted to point out, and this is a subtle but kind of in my opinion, kind of a big thing, is the number of nodes that you can have on the network. Earlier we were talking about data payload per device, but now we're talking about how many devices can you have out there. And I mean, you'd be able to better answer than I about Profinet or Ethernet IP, but from my understanding, on some of those networks, if you have 20 nodes or more, that's like a really busy network. Like you're starting to get worried about all these propagation delays that we talked about earlier. All the stacking delays and converting delays, things like that. So you have to limit the number of nodes. So EtherCAT is provisioned, no kidding, to go up to 65,535 nodes per network. So per one master scanner, you can have 65,535 slave devices out on the network right now. Okay, is that an academic number? I'm not going to lie. I have never seen a network that large. However, that's just because I haven't seen a network that large. It doesn't mean that it isn't provisioned for it. So it's ready to go for something that large and that scalable. I just personally, I haven't seen one that large yet. So yeah, that's kind of one of those head shaker kind of, did he really just say 65,000 devices on one network? How does that even work? Like what? Yes, that's how it works. And it works that way because of the packetization of the framework is so efficient. That's actually how it works. So briefly, just getting over some different technologies. So I kind of just threw these in to make sure that our audience knew that yes, EtherCAT is Ethernet based, and it's very similar to other Ethernet based topologies, or excuse me, some technologies. It has safety over EtherCAT FSOE. It functions a little bit different than SIP safety. It's more closely related to a ProfiSafe. Because I believe there's an ISO standard, and I apologize, I don't remember exactly what the ISO standard is, but they both comply to that same standard, so they're relatively similar from 10,000 feet type of thing. But yeah, you can just like SIP safety, you can integrate non-safe and safe devices all on the same network, which makes it very convenient as far as where you have to wire your e-stop back to, or how do you troubleshoot your e-stop because it goes through this JBox and that JBox and this JBox. Well, in this kind of case, and really any safety over the wire case, the idea behind the design is you put the I/O as close as possible, reducing the risk of broken cables and opens and shorts and things. To get to your actual input or your output. So this is the same. It works very similarly. And so yeah, just wanted to throw that out there that yes, this is also part of the EtherCAT package. EtherCAT P. So EtherCAT P, power over EtherCAT. This is something fairly new. Back in 2006, when I was first learning about this and using the very first EtherCAT devices, there wasn't EtherCAT P. Now the standard has 100% not changed at all. So all the packaging, all the devices, all the standard is the same, except now physically, if these devices have, it's the same. 4 copper wires, right? So really you have your RxTX plus and your RxTX minus. That's any Ethernet technology. That's how it works, right? So what they've done is they're now adding power to those two circuits, right? So Rx plus, Rx minus. Now these are your two circuits. So your control power circuit and your output power circuit are on those two, and now multiplexed on top of that is the EtherCAT signaling, right? So really it now you have power and comms all in one cable. And yes, so is it in one cable? And how does that one cable actually multiplex all this? I don't have the answer to that. It's just, again, this is all information from the ETG. So, but this is how it works. You do have those scenarios to where it's very, very convenient. Yeah, I have to run a cable for power, but hey, it's only one cable, and it has power and comms both on it, right? That's really the idea. Looking at the different topologies, again, the topologies the physical topology does not matter to the packaging because it's going to make a round the horn trip anyways. But just different ways to inject power for EtherCAT P within your network, right? So yeah, I just wanted to talk about that. Now, I'm not going to spend a lot of time on this technology called a distributed clock, but a distributed clock, what that does is, even with EtherCAT and this very efficient train of messages or this train of data on it, and we spent a lot of time on how the packetization works. Even with that, there actually is, like, remember I was talking about that train and train carrying people, and yes, it has to stop for a couple minutes per stop and all this, but the electronic one doesn't really stop. It doesn't stop, but it does slow down. There is a delay in the message being read in and the data being copied to the packet on the fly. There is a delay for that. However, the thing about a distributed clock, what I'm talking about here is if you know what that delay is, and you can prevision for that delay. So on the screen right now, what we're looking at is a very large network, and this very large network goes from it's 300 nodes. So excuse me, node number 1 to node number excuse me, node number 1 to node number 300 with 120 meters of cabling and I/O between. There's a lot of potential propagation delay in the passengers getting off the train and getting on the train, right? And so that's okay. We know what that, if you know what the delay is, then you can predetermine when to send out or pre-send out different messages. So to have absolute synchronized motion between 300 nodes within the jitter, so it's simultaneous within 15 nanoseconds. There's a picture on a graphic with a scope capture on it, and there's 20 nanoseconds of jitter, and the on and off signal here is spot on, and it's a scope capture, right? I mean, so everybody understands what that looks like. And the on and off, the falling edge signal is exactly happening at the same time with a 20 nanoseconds of jitter. And the way that happens is the distributed clock. Distributed clock is, hey, I know what my delta T is between my master scanner and node 1, master scanner, node 2, so on and so forth. And because I know what that deterministic delay is, if it's the same every time, I can compensate for that. And so that's really what this distributed clock is. And again, I don't really, I mean, maybe distributed clocks is a big thing. So that's almost a whole nother topic. But for this particular webinar, our podcast, excuse me, I don't really want to get into that unless Shawn, you have a real burning desire to learn more about how distributed clocks work with ultra high precision synchronization.
No, I think it's good to know that this feature's in there, and I think most people can conceptually understand that if each device has a clock built in, it knows when the packet comes in and it knows when the packet goes out. So that delta T is always known and can be compared, over time. So you're by real time, you know the performance of your network, because every device is a smart device and capable of making use of distributed clocks. So I think that's a good, that somebody who wanted just to know if that feature was in there, now you do.
Right. Well, and I threw that in there because you can get real deep real quick. But if you kind of Google it and go, I listened to this podcast and I don't know what that guy was talking about, I'm gonna Google this, and one of the first things you're gonna see is distributed clocks and how that all works. I just wanted to bring it up just for that reason. Hey, it exists. We can always get deeper into it, but yeah, that's really the 10,000 foot view on how distributed clocks work. A system overview. So how does this work with like a whole line? So people might be thinking, okay, cool, EtherCAT, I get it. It's for a specialty machine, and like I said earlier, like a specialty machine only in the pharmaceutical industry or something. Well, no, even though that might be the perception, that's not reality. And so just for the folks that are gonna hop on later and take a look at this whole system overview, we have a system of 5 different PLCs and how these different PLCs interact, all real time with EtherCAT, different technologies. I'm not going to spend a lot of time on that, but just kind of how does this really work? So like in a whole manufacturing line, not just a packaging machine or whatever, but the whole line, how does that work? What does it look like? And it's just a great graphic to kind of show you an overview of that. So in the beginning, I promised to give you some stats and things. So, hey, I'm just not making this stuff up. It isn't just this one-off, this guy from SMC. He's talking about EtherCAT, and I don't even know what the heck that guy was talking about. He's just making it up. Well, so from the ETG, the governing body of EtherCAT, the global market share of all Ethernet-based technologies currently, EtherCAT has 26% globally. So maybe we're looking at, and I'm one of those people that I look around and go, yeah, I haven't really seen a lot of those machines. I see a lot of whatever I see in my region, right? So I see a lot of Profinet. I see a lot of EtherCAT. I see a lot of Ethernet IP, maybe Modbus TCP, which Modbus TCP, it's an oldie but a goodie that's still around. In fact, I talk to people about that, probably once every other week still. So it's still around, but this is a nice little graphic just showing, like, for example, I don't know where these numbers came from other than I got them from ETG, EtherCAT Technology Group, ETG. Profinet worldwide is about 22% market share. EtherCAT's 26% market share. Ethernet IP globally is about 17% market share. And the rest is all kind of in smaller market shares. So PowerLink and Modbus TCP and Circos 3 and raw Ethernet TCP IP covers up the rest of it. So to give people an idea of kind of a global reach, that's really what this is looking at. So not just one region or one particular country, but this is a global thing. So membership, I was talking about that earlier. And again, this isn't a pitch to sell EtherCAT. This is just kind of an understanding of, well, this isn't just a one or two company thing. There's a lot of companies. So as of April 12th, 2021, there is 6,210 ETG members from 68 countries. So over 6,000 members. So what these members are, they're vendors. So IO vendors, drive vendors, safety cameras, you name it. Those are the people that have gone to ETG and said, hey, we want to be part of this. We want to develop this technology. Help us develop this thing. So there's quite a few of them, just to show you kind of an idea on a. And again, this is a graphic. It's a very, very, very busy graphic showing, hey, this is on the master side. So of that, 6,200 vendors, there's 224 of them are the master side, so the scanner side, right? Now, some of these also have the slave side too, for sure, but not all of them. Just showing just a quick graphic of that. The drive vendors, so as you can about imagine, with this real-time efficiency, the drive folks, the digital servo people, are really, really interested in this, and this is kind of one of their go-to networks. But certainly, as I was saying earlier, SMC is 100% part of that, and that's where we're seeing this growth is on our drive side. SMC has drives. Yes, we do. We'll get into that in a second, but just to show that yes, this is a real thing, and absolutely we're proud to be part of it. So the EtherCAT also has well over 1,000 registered IO product vendors. So these different vendors throughout the world that make different IO solutions, they make it on EtherCAT. So really the idea here is this isn't just me that works for SMC saying how great EtherCAT is because that's how pneumatic valves work the best on, even though they do work quite well on EtherCAT. It's a huge big picture of a lot of different people throughout the world, and like I said, it's not even just a regional thing. So it's not just oh yeah, that happens in Europe, or oh yeah, that's a Japanese thing, or so on. This isn't really like that. This is everywhere. So North America, you name it, that there's vendors adding to this list every day. So Just kind of wanted to go through that just to show, hey, this isn't a one-trick pony deal. SMC is of course 100% supportive of EtherCAT. So we actually have our own landing page for EtherCAT. And for those of you that are gonna hop on and look at this graphic, it's just a landing page. I got the link right there. And in fact, if you just go to www.smcusa.com, type in EtherCAT, hit enter, it'll bring you right to this landing page, which will go through all of the products that SMC offers in EtherCAT. And again, like I said, SMC, we do not make a PLC, or when we don't want to, right? So we're not part of that world. So whatever PLC that you pick, if it does support EtherCAT, absolutely, we have the other side, right? So the I/O solution or the digital servo solution, that can be plugged right in and it'll work because everything all complies to the ETG standard. So yeah. So in the valve world, of course, that's what we're kind of known for. There's 4 flagship series of valves that are ranging from small flow to like, a 0.3 CV to over 2 CV of flow. Well, that all plugs right through an EtherCAT. I guess you'd call it a bus coupler or a head unit, a comms unit that bolts right to the manifold, as well as our I/O solutions that are also part of the valve manifold, making it pretty convenient and easy to land sensors and things right next to your valve pack. The digital servo world, and I kind of alluded to this a little bit earlier, is that hey, people don't even know SMC. You're the stick in the can, right? The pneumatic actuator people in the valves, which is absolutely true. But we also have a giant line of pneumatic, or excuse me, of not pneumatic, so of electric stepper and servo actuators. There's 11, actually there's over 11 lines. So different styles like, do you need a rotary? Do you need a gripper? How about a rod style, compact style, things like that. We have all that, and every one of those products has at least 3 or more sizes, and in each size there's at least 3 or more ball screw pitches. So you can really get dialed into exactly what you want. The cool thing is if we can figure out the mechanic side of that, all of it complies to EtherCAT. Well, it complies to Ethernet IP, Profinet, EtherCAT, but absolutely, we support EtherCAT. So that's part of it for sure.
I think that's an important for those listening and not familiar with SMC. They do also support beyond EtherCAT. They also support Profinet, Ethernet IP, CC Link, IO Link. So don't come away from this presentation. I do appreciate that Nathan's volunteered to do the EtherCAT presentation, but you'll see on the automation show, we have shows coming up where we're using their products on Ethernet IP and other networks too. So I wanted to throw that out there because it's listed in all the slides, but for those listening, they may I don't want them to come across thinking that SMC is only supporting EtherCAT. You're supporting all the major networks.
That's exactly right. So traditionally we support over 16 different networks. And this EtherCAT is just one of those 16. But absolutely. So thank you for adding that. It has to do with SMC's place in the market, is because we don't sell a PLC. We are not pushing a particular field bus solution because we don't sell a PLC. Our strategy is, hey, Mr. Customer, what do you want, right? And we don't have a preference. If you want to go Rockwell, if you want to go Siemens, if you want to go to something else, whatever, that's fine with us. But we want to make sure our products will hitch in to what you pick. And so that's kind of our strategy a little bit on that. Coming soon. So there are some things in development that I can't show you, but it has to do with some safety, some safety with some valves. There are some things to do with efficiency, some IoT, different solutions, but with IoT comes efficiency or or at least the knowledge of what is efficient, what is not efficient, right? It's the whole, if a tree falls in the woods and nobody's there to hear it, nobody cares, right? So you gotta write it down, right? If it's not written down, it never happened. If it's not recorded, if it's not digitally recorded, it didn't happen. So those kind of things are soon coming, and yes, they are soon coming, not only on EtherCAT, but certainly EtherCAT, but also in Ethernet IP and some Profinet devices coming down the pipeline. So so with that, Shawn, did you have any other, overwhelming kind of burning questions about EtherCAT, or something that maybe you want to think about? Maybe your audience would kind of go, I don't know about that. I don't know about that guy. Insert question here. Do you kind of have anything like that?
Well, I really want to thank you for coming on. It really gives us a good overview of not only, that EtherCAT is works with Ethernet devices. I think you kept saying 802.3. I think it was, totally 100% Ethernet compatible. It came out, I believe it was 2003, so it's been around for a long time. And the big difference here is because of the design of how the frames and packets and how it works, and limiting a lot of the fluff that gives other features other products lots of features, but may not be needed on an IO network. I think you really give us a good idea of how EtherCAT can be so fast and support so many nodes. And I think this presentation did a good job showing that. One of the things I've noticed is that EtherCAT is from the list you had, extremely popular amongst almost all industrial automation providers, but there's a couple who haven't adopted it yet, it seems. A couple of the big names. So hopefully we see they jump on board too, because those big names have jumped on the IO links and they've jumped on the other networks. So a couple
Yeah,
of the biggest
that's
boys out there don't have like EtherCAT scanners or EtherCAT adapters for
right,
their IO.
right. Yes, no, you're exactly right, and I do hope that someday they do hop on board. But without saying it, there is a strategy involved, and let's face it, we're not doing this for our health. We're doing this for our companies, or we're doing this for our career, for our income, right? And so there are some different strategies out there that certain vendors, they probably don't want this. It's kind of a cut off your nose to spite your face kind of situation, but that's okay. And look, like I said, I started out saying I'm not judging, and I'm not pitting one against the other one. But yes, you're right. There are a couple of those, the big players out there that haven't really adopted it yet, and that's has to do with their own market share and things like that. So, but however, it's my understanding that the ETG won't turn anybody away. This is an open technology that anybody can sign up for and learn more about, and then develop products against it. So the hope is that hey, maybe someday that they could do that. But again, I want to leave my personal opinions out of it, and so I'm going to, and I just yeah, that was a great observation.
Yeah, it would be nice to get that type of speed with the IO or the drives or the servos without having to go to gigabit, having to rip everything out and go to gigabit. So it's definitely something I hope vendors will look at who are not on those lists. There were a lot of vendors on there. There were a lot of vendors, but some of the biggest we work with have shied away from it so far, appears. Just going by the latest presentation. And I just if not that they're listening, but if they were, I encourage them. The more tools we have in our toolboxes as controls engineers or design engineers, the better it is. And when we need super high speed I/O, this could be one way, especially with all the controllers on the market being so phenomenally fast that the bottleneck is often the I/O. So it'd be nice to have everybody on the same field. But in any case, Nathan, that was an awesome presentation. Thank you, and SMC, for giving us this in-depth look at, or introductory look at, EtherCAT. I hope the audience enjoyed it. Guys, let me know what you thought. And again, thank you for taking all the time. I know it took hours to put this together. So Nathan, thank you so much, very much, for doing this for us.
You're very welcome. And please, if there is any questions or whatever, let me know, and I'll do my very best to answer those questions that any of your audience members might have.
Well, thank you again. I really appreciate it.
You bet.
Well, I hope you enjoyed that. I did, and I really want to thank Nathan for taking time out of his busy week to put that presentation together and bring us all up to speed on EtherCAT. With that said, if you're watching on YouTube, please consider giving us a like and a sub. And if you're listening to the audio-only edition over at iTunes or Spotify or TuneIn or iHeartRadio or Pandora or wherever, please consider subscribing and giving us a like, because it really does help us reach more listeners as well as find new potential guests. With that said, I want to wish you all a very safe, happy, and healthy week. And until next time, my friends, peace.